Module 3, Lecture B, Probability Intuition. By the end of this lecture, you will be able to explain probability as a measure of uncertainty about events, compute simple probabilities from counts and small examples, and interpret basic conditional probability statements in plain language. Understanding uncertainty, events and outcomes. To understand probability, it helps to distinguish between outcomes and events. An outcome is a single specific result of an uncertain process, like a coin landing heads or a die showing a particular number. An event is a collection of outcomes that share a property, such as the die roll being even or a student passing an exam. In real situations, events like rain tomorrow are treated as sets of possible outcomes, and analyzing these sets allows us to reason clearly about uncertainty and make better decisions. Probability is assigned to events, not to the abstract process that generates outcomes. When we flip a coin, predict the weather, or evaluate a product launch, many detailed outcomes are possible. But we define events based on the questions we care about. For a product launch, the event might simply be earning a positive profit. The probability of that event then represents our belief about how likely that result is among all possible outcomes. In this way, probability connects complex real-world outcomes to simpler events that guide our decisions and expectations. When working with probability, it is essential to define events clearly so there is no confusion about what each probability refers to. The same real-world situation can involve different events, such as a positive medical test, actually having a disease, or both happening together, and each has its own probability. In a hiring context, events might include receiving a job offer, accepting it, or both occurring. By carefully specifying which event we mean based on detailed outcomes, we can describe and compare uncertainty in real situations accurately. Probability scale. Think of probability as a scale that runs from impossible to certain. At one end are events that cannot happen, like drawing a red card from a deck that has only black cards. At the other end are events that must happen, such as rolling a number less than or equal to 6 on a standard die. Most events fall between these extremes, where we judge them as unlikely, likely, or about equally likely. This way of placing events along the scale helps us understand probability even without using exact numbers. In probability, we describe uncertainty by assigning numbers between 0 and 1 to events. A probability of 0 means the event is impossible, and a probability of 1 means it is certain. Values near 0 represent very rare events, while values near 1 represent events that almost always occur. A probability around 1/2 means an event and its opposite are about equally likely, such as a fair coin landing heads or tails. Using these numbers lets us compare uncertainties more precisely than with vague terms like maybe or probably. A probability scale is a way to describe how likely events are, using numbers between 0 and 1. For example, saying there is a 30% chance of rain means the probability is 0.3. And a medical test that is 95% accurate has a probability of 0.95 of giving the correct result. Even your confidence in arriving on time can be placed somewhere on this scale. Using this common numerical language helps us compare and reason about uncertainty in many different situations. Probability from repeated trials. To understand probability, imagine repeating an uncertain event, like slipping a coin or checking the weather, many times. Each flip or day is a trial with possible outcomes, such as heads or tails, rain or no rain. With only a few trials, the results can look misleading, like getting mostly heads or several rainy days in a row. But as you repeat the trials under similar conditions, the results settle into a stable pattern. This long-term pattern is what probability measures, the regularity that appears over many repetitions of an uncertain event. When you roll a fair six-sided die, only a few times, the number of sixes you see can vary a lot just by chance. But as you repeat the experiment hundreds or thousands of times, the fraction of rolls that show a 6 settles down to a stable value. The same idea applies in real situations, such as measuring how often light bulbs fail or how often treatments succeed in hospitals. Over many trials, the long-run frequency of an outcome becomes stable, and we interpret this stable frequency as the probability, which expresses our uncertainty before any single trial. Thinking about probability through repeated trials helps us see the difference between what is merely possible and what is actually likely. A fair coin could land on heads many times in a row, and a small clinical trial might show a very high success rate for a new drug just by chance. However, when we look at thousands of coin flips or large medical studies, we get a more accurate picture of the true underlying probabilities. In this way, probability describes the long-term patterns that emerge from random events and quantifies the uncertainty of any single outcome. Python code: probability from repeated trials. This script uses repeated random trials, like flipping a coin many times, to illustrate how probability works. As we simulate more and more flips, we track how often each outcome occurs. The goal is to show how individual results are uncertain, but the long-run frequencies settle into stable patterns that reflect the underlying probabilities. We begin by importing the random library so we can generate random numbers and outcomes, which we need to simulate coin flips. We also import the plotting tools from Matplotlib, using them to create graphs of our simulation results. These visualizations help us see how the probabilities behave as we repeat the coin flip experiment many times. We use a deterministic seed in the random library so that the random values we generate are always the same each time we run the script. This makes the sequence of random numbers reproducible. Reproducibility is important because it allows us to debug more easily and verify that our results are consistent. Without setting a seed, each run could produce different random values, making it harder to track down issues or confirm findings. We define a function to simulate many coin flips and use it to estimate how often heads appears. Inside this function, we set up a counter that starts at 0 and increases by 1 each time we get heads. This running count lets us track the total number of heads as we go. From this, we can calculate the proportion of flips that come up heads during the simulation. We create an empty list to record the proportion of heads after each coin flip. After every flip, we update this list with the current running proportion of heads. This lets us see how the observed frequency of heads changes as we perform more trials. By examining this list, we can study how the empirical probability approaches the theoretical probability for a fair coin. We run a loop that goes through each trial, from the first trial up to the total number of trials. In every trial, we simulate a coin flip by randomly choosing between heads and tails. This random choice function selects either H for heads or T for tails. Because each outcome is equally likely, this models a fair coin flip in each iteration. This part of the code checks whether a coin flip comes up heads, and if it does, it increases the heads counter by 1. By updating this count each time heads appears, the program keeps an accurate running total. This running total is then used to calculate the proportion of heads across all the coin flip trials. We find the current proportion of heads by taking the number of heads observed so far and dividing it by the current flip number. This calculation gives the fraction of all flips up to that point that have resulted in heads. It tells us, at each step in the simulation, what share of the outcomes have been heads. We record the current proportion of heads after each coin flip and add it to a running list. This lets us see how the proportion of heads changes as we perform more flips. By storing each value, we can later study or visualize how these proportions evolve across all the trials. The function finishes by returning a list of running proportions, where each value is the proportion of heads observed up to that trial. This means that for every coin flip, you can see how the fraction of heads changes over time. Having this list makes it possible to analyze or visualize how the proportion of heads evolves across the entire sequence of flips. We use 200 coin flip trials to balance accuracy with practical runtime. This number is large enough to show how the probability of heads converges as we flip the coin repeatedly, but small enough that the simulation runs quickly. As the number of flips increases, we can clearly see the proportion of heads begin to stabilize over time. We run a coin flip simulation function with a chosen number of trials, and it records the proportion of flips that come up heads after each trial. This gives us a list showing how the relative frequency of heads changes as more flips are performed. Pausing. By examining how these proportions evolve and eventually stabilize, we can see how repeated experiments reveal the underlying probability of getting heads. We first check whether the list of running proportions of heads has the same length as the number of trials we plan to run. This confirms that the simulation produced the correct number of results. If the lengths do not match, we raise a value error to indicate that something went wrong and the list of running proportions has an unexpected size. We create a list of trial numbers to use as the horizontal axis in our plot. This list is generated from 1 up to the total number of trials so that each trial has its own index. Using these indices lets us accurately plot how the running proportion of heads changes as the number of trials increases. We begin by creating a new plotting window using a figure function from a graphing library, which gives us a blank canvas for our visualization. We set its size to 6 by 4 inches so the plot is easy to see. This prepared figure will be used to display how the running proportion of heads changes over repeated trials and how it converges as more data is collected. We use a plot of the running proportion of heads across coin flip trials to see how this proportion changes as more flips are performed. This visualization shows how the observed frequency of heads evolves over time. As the number of flips increases, the plot helps illustrate the idea of probability as a long-term relative frequency. A horizontal line is drawn at the value of 0.5 to show the theoretical probability of getting heads with a fair coin. It is colored red and made dashed so it stands out from the rest of the plot. This line is labeled as the theoretical probability, allowing viewers to easily compare the simulated results with the expected outcome. We use the xLabel function in Matplotlib to set the label for the horizontal axis of the plot. In this case, the label is number of coin flip trials, which tells us that the x-axis shows how many times the coin has been flipped in the simulation. This clear label helps viewers quickly understand what the horizontal axis measures and gives context for interpreting the data in the plot. We label the vertical axis of the plot as the proportion of heads so far. This tells the viewer that the height of each point shows the fraction of coin tosses that have resulted in heads up to that trial. In other words, the y-axis represents how the cumulative proportion of heads changes over the sequence of trials. We choose a title for the plot that emphasizes probability as the long-term frequency observed when flipping a coin many times. The title links the randomness of each individual flip with the stable pattern that emerges over many trials. This gives listeners context for how the visual data represents the idea of probability as a long-run behavior, rather than a single random outcome. The code uses the legend feature from the plotting library to add a legend to the graph. This legend distinguishes the empirical line, which shows the running proportion of heads, from the theoretical line, which shows the expected probability for a fair coin. Including this legend is important for clarity, so viewers can easily identify and compare the two lines. We look at the proportion of heads after the first 10 coin flips by taking the 10th value from the list of running head proportions. This value gives an early snapshot of how the proportion of heads is changing over time. By examining it, we can start to see the initial variability in the outcomes of the coin flips. We look at the proportion of heads after 50 coin flip trials to see how the simulation behaves partway through. This snapshot shows how the proportion changes as we collect more data. By doing this, we gain insight into how the observed proportion gradually moves toward the theoretical probability of getting heads. After completing all 200 coin flips, we calculate and print the final proportion of heads. This value shows how the observed proportion moves closer to the theoretical probability of 1/2 for a fair coin as the number of trials grows. In this way, the result illustrates the long-term behavior of the random process. We then use the plotting library's show function to display the graph. This lets learners see how the proportion of heads changes as more coin flips are added. By watching the plot, they can observe that the proportion gradually settles near the theoretical probability. This visual feedback helps confirm how the results converge as the number of trials increases. This script simulates 200 coin flips to show how probability behaves over many trials. It tracks the proportion of heads after each flip, which jumps around at first, but gradually settles down. As the number of flips increases, this proportion moves closer to the theoretical value of 50%, represented by a dashed reference line. By around 50 flips, it starts to stabilize, and by 200 flips, it is usually very close to the expected value. This demonstrates the idea of long-run frequency and probability, where random outcomes become more predictable when repeated many times. Probability from counts, favorable and total cases. To calculate probability in a given situation, think in terms of favorable cases and total cases. The total cases are all possible outcomes, and the favorable cases are the outcomes you care about. For example, when drawing a heart from a deck of cards, all cards are total cases and the hearts are favorable cases. The probability is the number of favorable cases divided by the number of total cases, assuming each outcome is equally likely. This way, probability becomes a straightforward counting problem. Probability describes how likely an event is by comparing the number of favorable outcomes to the total number of possible outcomes. For example, if a box has 10 markers and 3 are blue, the probability of drawing a blue marker is 3 divided by 10. The same idea applies in a survey where 5 out of 20 people commute by bicycle, so the probability that a randomly chosen person is a cyclist is 5 divided by 20. In each case, you find probability by taking the count of the desired outcome and dividing it by the total number of cases. The idea of favorable and total cases helps us understand probability in many real situations. In quality control, a batch with 50 items and 4 defects has 50 possible cases and 4 favorable ones if we want to pick a defective item. In sports, if a player makes 30 out of 40 free throws, each shot is a case, and 30 are favorable. By comparing favorable outcomes to all possible cases, we turn raw counts into a probability that describes how likely an event is to happen again. Relative frequencies. Relative frequency connects probability to real-world data by looking at how often an event actually occurs over many trials. Instead of using only theoretical models, you record outcomes, such as counting how many days it rains in a month to estimate how likely the event is. If it rains on 9 out of 30 days, that ratio serves as an estimate of the probability of rain based on your observations. In this way, relative frequency turns raw counts into a practical measure of how common an event is in your experience. When we calculate probability using relative frequencies, we use observed data as an estimate of the true chance. For example, if 6 out of 200 light bulbs are defective, we treat 6 divided by 200, or 3 out of 100, as the probability that a randomly chosen bulb is defective. Likewise, if a player scores 38 out of 50 penalty kicks, that fraction is used as the player's estimated chance of scoring. In both cases, we turn counts into fractions of the total and interpret these as empirical probabilities based on past outcomes. Relative frequencies become more reliable as the number of observations increases. With only a few trials, like flipping a coin 4 times, the results can be misleading. But with many trials, such as 400 flips, the proportion of heads gives a much clearer indication of the true probability. The same idea applies in real situations, such as tracking bus arrival times or online shopping behavior, where collecting more data leads to better estimates of how likely an event is to occur. Python code, relative frequencies. This script demonstrates how probability can be understood through relative frequencies. It uses simple counts from repeated random experiments to estimate how often different outcomes occur. As you run the steps, you can observe how these frequencies gradually get closer to the true underlying probabilities. We begin by importing the random module from Python's standard library. This module lets us generate random numbers and make random choices. Using it, we can simulate random events such as coin flips. This adds controlled randomness to our experiments so we can model real-world probabilistic situations. We set a fixed random seed so that the sequence of random numbers is always the same each time we run the script. This makes the random choices predictable and repeatable. As a result, we can reliably reproduce our results, which is important for checking correctness. It also makes debugging easier because the program's behavior does not change from one run to the next. We define a function that simulates flipping a coin a chosen number of times, and it takes the number of flips as its single input. Before running, the function checks that this input is a positive whole number. This assertion acts as a safeguard, making sure the function is used correctly. If the input does not meet this requirement, the function stops instead of running with invalid data. We begin the simulation by creating a counter to record how many times the coin lands on heads. At the start, this counter is set to 0 because no flips have occurred yet. Each time we flip the coin and get heads, we increase this counter by 1. This simple setup lets us track the total number of heads over the entire series of coin flips. The code runs a loop for the chosen number of coin flips, and each time it randomly picks either heads or tails. Whenever the result is heads, it increases a counter that tracks how many heads have occurred. In this way, the loop simulates flipping a coin many times and records the total number of heads. The function outputs 2 values, how many heads occurred and how many total flips were made. Having both pieces of information lets us see not just the result we care about, but also the size of the experiment. This combination is important because it provides the data needed to compute probabilities or relative frequencies later on. The relative frequency function calculates how often an event occurs compared to the total number of trials. It takes the event count and the total trial count as inputs. Before computing, it checks that the total number of trials is greater than 0 and that the event count is not negative and does not exceed the total. These checks ensure the inputs are logically consistent and help prevent errors in the calculation. Relative frequency is found by dividing the number of times an event occurs by the total number of trials. This calculation gives a proportion as a decimal value. It tells you how often the event happens compared with all observed outcomes. This function returns the relative frequency, which is the event count divided by the total number of observations. It tells you how often an event occurred compared with all trials. This value serves as an estimate of the event's probability based on the data that were observed. We run a small experiment by using a coin flip simulation function with 10 flips. This function randomly flips a coin 10 times and counts how many times heads occurs. It stores the number of heads and the total number of flips, which is 10. With these values, we can later compute the relative frequency of heads in this small sample. We now compute the relative frequency of heads from our small experiment by using a function that takes the number of heads and the total number of flips. This calculation gives us the proportion of flips that resulted in heads out of the 10 trials. That proportion serves as an estimate of the probability of getting heads based on this small sample. We model a larger experiment by using a function that flips a coin 200 times and returns how many heads occurred and the total number of flips. We store these results so we can examine the proportion of heads in this bigger set of trials. By increasing the sample size, the observed frequency of heads becomes more stable and gives a better estimate of the true probability. To find how often heads occur in the larger coin flip experiment, we use a function that calculates relative frequency. We give this function two inputs, the number of heads and the total number of flips. It returns the proportion of flips that were heads. This value summarizes how frequently heads appeared in the larger sample. We display the results of the small experiment by printing how many heads occurred and how many total flips were made. This gives a quick numerical summary of what happened in the trial. Seeing these raw counts helps us understand the outcomes before we move on to calculating any probabilities. We now print the relative frequency of heads from our small experiment. This value tells us how many of the 10 coin flips came up heads, expressed as a proportion of all flips. By looking at this result, we can see how close our observed frequency is to the theoretical probability of getting heads with a fair coin. The code reports the outcome of the larger coin flip experiment by printing how many heads occurred and how many flips were made in total. This gives us the raw counts from the experiment. Seeing these numbers first helps us understand the basic results before we move on to calculating the relative frequency of heads. We report the relative frequency of heads from the larger coin flip experiment to see how often heads occurred compared to the total number of flips. This value shows how close the observed frequency is to the underlying probability. By using a larger sample size, we can better judge how stable and reliable our probability estimate is. The message explains how sample size affects probability estimates. It states that larger samples usually give more reliable and stable estimates because they are based on more data points. This helps link the counts observed in experiments to the underlying ideas of probability and shows why increasing the amount of data improves our confidence in those estimates. This script uses simulated coin flips to show how relative frequencies approximate probabilities. With a fixed random seed, it first flips a coin 10 times, counts how many heads occur, and computes the relative frequency of heads. It then repeats the experiment with 200 flips, where the relative frequency of heads is more stable and closer to the theoretical probability of 50%. Overall, It demonstrates that larger sample sizes give more reliable probability estimates, illustrating the law of large numbers. Class proportion examples. Class proportions connect probabilities to familiar group categories. If you know what fraction of a class belongs to a certain group, such as international students or biology majors, that fraction directly gives the probability of randomly selecting someone from that group. In other words, the chance of picking a student in a specific category is equal to the proportion of the class that category represents. This turns simple counts of students into useful probability information about individual selections. Think of a group of students divided into categories such as engineering, business, and arts. The probability of randomly selecting an engineering student is the number of engineering students divided by the total number of students. The same idea applies to any other trait, like commuting habits or year of study. In this way, probability is simply a standardized way to express how often each category appears within the whole group. Class proportion reasoning applies to any situation where you have categories within a larger group. By looking at the proportion of individuals in a category, you can interpret that proportion as the probability of randomly selecting someone from that category. This works in settings like companies, where you might focus on departments or work arrangements, and in public health, where you might look at age groups or vaccination status. Using class proportions lets you move smoothly between raw counts, proportions, and probability statements, which is essential for data analysis and decision-making under uncertainty. Understanding conditional probability. Using given information. Conditional probability is about updating how likely an event is once you know that something else has already happened. Instead of asking about the overall chance of an event, you focus on the probability given a specific condition. The key idea is the phrase "given that," which tells you what information to use and what to ignore. For example, knowing there is a storm at the destination airport changes how you judge the chance of a flight delay. Overall, conditional probability is simply a structured way to adjust your expectations when new facts become available. Conditional probability means focusing only on cases that meet a specific condition when judging how likely something is. For example, when we talk about the chance of having the flu given a high fever, we only look at people who already have a high fever, not everyone. In everyday life, we do this when a manager judges an applicant's chances after they pass a skills test, or when a driver predicts traffic during rush hour. Each condition narrows the group we consider, and our probability should always be based on that restricted group. When working with conditional probabilities, rely only on the information that is explicitly given and avoid adding extra assumptions. If a student passes a difficult exam, base your reasoning on the fact that they passed and typical study behavior, not on unmentioned help like special tutoring. If rain is predicted, given an overcast sky, do not mix this up with the chance of rain on a clear day. Always focus on the stated conditions, apply them to the correct context, and judge probabilities within that limited scope. This disciplined approach is essential for understanding and explaining conditional probability correctly. Event dependence basics. Conditional probability describes how the chance of one event can change when we know that another event has occurred. Our beliefs are updated based on new information. For example, seeing someone with a backpack and textbooks might make you think they are a student. But if you then see them enter an elementary school and greet children, it becomes more likely they are a teacher. This shift in likelihood, caused by additional information, is the core idea behind conditional probability. In everyday life, we often deal with events that affect each other's likelihood without formally thinking about probability. For example, if you know nothing about a person, you might have a rough idea of how likely they are to have high blood pressure. If you then learn they are over 70 and have a sedentary lifestyle, this new information increases that likelihood, showing the events are dependent. In contrast, learning their favorite color does not change your judgment about their blood pressure. So those events are independent. Dependent events influence each other's probabilities, while independent events do not. Understanding whether events are dependent or independent is important when interpreting conditional statements in real situations, such as risk assessments or forecasts. For example, a higher chance of rain when a storm system is approaching shows that these events are dependent. In business, knowing that a customer has added items to a cart can increase the likelihood of a purchase, since past actions can influence future behavior. Conditional probability describes how one event changes the likelihood of another, helping us interpret such statements more accurately in everyday life. Conditional probability in data. Conditional probability with real data asks, out of all cases that meet a certain condition, how many show a particular outcome? You can imagine a spreadsheet of people or events, then filter it to include only rows that satisfy the condition you care about. Within that filtered subset, you look at how often the outcome occurs. For example, if a university tracks whether students live on campus and join clubs, you might ask what fraction of on-campus students are club members. That fraction is the conditional probability of being in a club, given that a student lives on campus. Comparing conditional probabilities across groups helps reveal patterns in data. For example, in a health survey, you can look at the probability of high stress among people who exercise regularly and compare it to the probability of high stress among those who rarely exercise. If high stress is less common in the regular exercisers, this suggests a relationship between exercise and stress levels. However, this kind of comparison shows association, not proof that exercise directly causes lower stress. Conditional probability helps us interpret data by focusing on a specific group within a dataset. In a medical testing context, one question is how many people who have a condition test positive, which describes the test's sensitivity. Another question is how many people who test positive actually have the condition, which tells us how trustworthy a positive result is. These two probabilities are different because one is filtered by having the condition and the other by getting a positive test. Understanding conditional probability means always being clear about which group you are conditioning on, rather than looking at the entire dataset at once. Python code, conditional probability in data. This script uses simple survey-style data to demonstrate conditional probability. It shows how to compute probabilities by looking at very small counts within filtered groups. The key idea is to interpret each probability as a proportion taken only from the subgroup that meets a specific condition. In other words, we focus on how likely something is given that a certain condition already holds. This part of the code makes sure the pandas library is available before the script runs. It assumes pandas is already installed in most environments, so no extra setup is usually required. However, if pandas is missing, it suggests a fallback approach where you can enable a small installation routine that uses the system's package manager. This precaution helps the script run smoothly, even in environments that do not already have pandas installed. We begin by using the pandas library, which is designed for working with data in tables. This tool makes it easy to organize, manipulate, and explore datasets. In this lesson, we will rely on pandas to handle a small dataset that helps us demonstrate ideas from conditional probability. We begin with a small dataset that records people's exercise habits and stress levels. It is stored as a dictionary, with one entry describing whether each person exercises regularly or rarely, and another entry indicating whether each person experiences high stress, using true or false values. This structure makes it straightforward to convert the data into a data frame for further analysis of the relationship between exercise and stress. We use the pandas library to build a data frame from the data dictionary, which stores information on exercise levels and stress indicators. This step converts the raw data into a clear, table-like structure. Organizing the data this way makes it much easier to manipulate, explore, and analyze in the rest of the script. We begin by displaying the dataset so we can clearly see the records it contains. First, we print a brief description that explains the data includes exercise levels and an indicator of high stress. Then we show the full data table or data frame so the actual values and structure are visible. This initial inspection is essential for understanding what information is available before moving on to any deeper analysis. We create a filtered version of the data frame that includes only people who exercise regularly. This subset is called the regular group and contains just the rows where the exercise level is marked as regular. Focusing on this group allows us to study conditional probabilities specifically for individuals who exercise regularly, without the influence of other exercise levels. We create a subset of the data that includes only people whose exercise level is classified as rare. This filtering step isolates that specific group so we can focus on them separately. With this subset, we can then analyze and compare the probability of experiencing high stress among individuals who rarely exercise. To find the probability of high stress among people who exercise regularly, we first look only at the subgroup of regular exercisers. Within this group, we count how many individuals report high stress. We then divide this number by the total number of regular exercisers. The result is the proportion of regular exercisers who experience high stress, which is the conditional probability of high stress given regular exercise. To find the probability of high stress among people who rarely exercise, we look only at the rare exercisers and count how many of them report high stress. We then divide this number by the total number of people in the rare exercise group. The result is the proportion of rare exercisers who experience high stress. This proportion is the conditional probability of high stress given rare exercise. We calculate and display the probability of experiencing high stress among people who exercise regularly. This tells us how common high stress is within that specific group. By having this probability, we can compare it with the probability for other groups, such as people who exercise rarely. This comparison helps us see how different exercise habits might be related to stress levels. We calculate the probability of high stress among people who rarely exercise by dividing the number of high stress cases in this group by the total number of individuals in the same group. This value represents how likely someone is to experience high stress if they exercise rarely. By examining this probability, we can see how stress levels are related to how often people exercise. The code produces a simple, plain language summary to explain the results. It reports what fraction of people who exercise regularly still experience high stress. This statement directly reflects the conditional probability that was calculated. Its purpose is to connect the numerical result to real-world behavior, so learners can more easily interpret what the data means. This script uses a small dataset on exercise and stress to illustrate conditional probability. It builds a table with each person's exercise level and whether they experience high stress, then splits the data into regular exercisers and rare exercisers. For each group, it calculates the probability of high stress by finding the proportion of people with high stress in that category. The output first shows the dataset, then the probabilities, highlighting how likely high stress is for regular versus rare exercisers in this simple example. In this lecture, you learn to explain probability as a measure of uncertainty about events, compute simple probabilities from counts in small examples, and interpret basic conditional probability statements in plain language. In the next module, Module 4, we will go over linear models. Thank you for your attention. See you all in the next lecture.